How's it going, ladies and gentlemen? Mr. Johnny here again. We're going to take a look at factors affecting solubility. So the question is, what factors affect how much stuff, science word would be solute, how much stuff can be dissolved? A few things we're going to look at is ion-solute interactions. So we're going to compare different solutes and solvents and how they interact with each other. We're going to take a look at temperature. We're going to take a look at pressure. And a question that we can answer by the end of this video is, why do scuba divers get the bends, which is a painful condition after they go scuba diving and possibly fatal? So first off, we're going to take a look at the solute-solvent interactions. And you got to remember that like dissolves like. So if we're taking a look over here, we have a polar solvent and we have an ionic solute over here. So we have charges, and charges are going to interact. So the more strongly they interact, the more stuff can be dissolved. It kind of makes sense, right? The more that they're like, hey, I like you, you like me, we can hang out, the more stuff you can dissolve in it. Whereas over here we have an example of water and oil, and we know that they don't really interact a whole lot because we have this polar molecule and this nonpolar oil or fat molecule, and they don't interact. So you can't really dissolve a whole lot of oil in water because there's not really much of a solute-solvent interaction. Whereas over here with the water and the salt, there is. So the stronger your interaction, the more stuff you can dissolve. Next thing we're going to talk about is temperature. So you got to remember that temperature is average kinetic energy. So the more that the temperature is higher, the more stuff is moving, which is good for solids. So if we're taking a look at solids and we have temperature and we have solubility, well, as the temperature goes up, so does the amount of solute that you can dissolve. Because the water molecule's got more energy, which means it can hold on to more of this stuff, right? It's going to be easier for it to separate out the chloride ion from the sodium ion because it's got that extra energy. Now, the opposite is true for gases. You can think of gases as trying to be trapped by the solvent. So if I had a container with water in it and I'm trying to trap as much gas into the water, well, the more the water moves, the easier it is for the gas to escape, right? So it does the opposite. As the temperature goes up, the solubility goes down for gases because it's, think about this. Gas wants to be free. It wants to spread out. It wants to get out of there. It wants to do its own thing. Water's like, nah, you're going to stay here. And the gas is like, all right, well, I got to find a way out. The more that the water is moving, the easier it is for the gas to escape. Whereas if the water was slower, well, the gas would have a harder time to get out of there. This is important when it comes to a couple of things. I want to take a look at nuclear power plants because they use a lot of water as coolant. So I want to first point out that here we have a reactor. The reactor is the nuclear reactor. It's got the radioactivity and stuff, and we have some superheated fluid that is going to heat up a steam generator. All right, but this fluid that's actually exposed to the radioactivity is not mixing with the water that's used to power the turbine. This is a completely closed system. So it's not like we're putting radioactive water out. We're just putting out hot water. So we use that heat to heat up some water, turn it into steam, turn a turbine, and make some electricity over here, power some houses. But then we still need to cool down all of that hot water. So here we have cooling water going in, and then it goes to these cooling towers over here to cool it off before it enters a reservoir and released back into the environment, cooled down and good to go. Now the question is, well, why don't they just put the warm water or the hot water back into the environment? Anybody who has a goldfish and accidentally killed them using a lamp, this is how you did it. Okay, so here we got some fish, right? And what do fish need? Say oxygen. Oxygen! Good job. All right, so we have oxygen dissolved in the water. And the fish are happy because they need to breathe that oxygen, right? So it goes in, goes through their gills, and they're like, yay, I'm a happy fish. Right? But what happens to the solubility if it were to get really hot? Let's say you had a goldfish in a goldfish bowl and you put a lamp on it because you want to look at it all night because you're just really excited to have a goldfish. By the way, these aren't goldfish, they're tarpon. I like tarpon, but I don't have any pet tarpon. But regardless, so you got some goldfish, right? You put it under a lamp and the lamp's heating it up. All right, well, let's think about this. We had oxygen dissolved in the fish bowl. We had oxygen dissolved in the water. And if it's getting hotter, there's going to be less oxygen in the water. The oxygen is going to escape, and you're going to be left with water that doesn't have a whole lot of oxygen. So what's that mean for your fish? Fish are going to essentially suffocate and die. So don't do that to your fish, right? You're kind of making them, in a strange way, drown. You're drowning your fish because they can't get enough oxygen in the water, and then they die. So that's why temperature is important to consider with gas solubility. So pressure. Well, what does pressure affect? I can tell you right now, pressure does not affect solids at all. Solids, pressure doesn't matter. But gases, it does matter. So if we have pressure and we have solubility, as pressure goes up, so does the solubility for gases, which kind of makes sense because you can think of it this way, right? If I got this container and I got some solvent, pressure is pushing those gas molecules into the water. It's forcing them to dissolve. So the higher the pressure, the more stuff we can dissolve. And the opposite is true. If you decrease the pressure, the solubility for the gases goes down, which is the issue when it comes to the bends. So mind my drawing. This is a scuba diver swimming. Yeah, right? So the scuba diver's got the scuba tank, and he's got a hose going up to him so he can breathe air, right? So what happens to scuba divers when they go down at depths? Well, the pressure goes up. So we got the scuba diver now deep underwater, and the pressure goes up. So the amount of gas that's dissolved in their blood goes up. So I'm going to draw a picture of, let's call it a blood vessel. It's an artery or something. So we got gas dissolving more into their blood as the pressure goes up. Right? Pressure goes up, the gas enters the blood, which is good because we need those gases like oxygen to keep our muscles going. So we got the scuba diver, and they're going around looking at things. And then after a while, some time goes by, and then go, it's time to go home. I'm running out of gas. I got to come back up to the surface. I gotta go home. I gotta get on a plane. I'm on vacation. This is great, but I got things to do. So they go back to the surface. The pressure goes down, which means the amount of gas that can dissolve also goes down. So what those gas particles end up doing on the way up is going, hey, there's less pressure. Let me get out of here. Let me get out of this blood. Let me no longer be dissolved and form gas bubbles. So it's the same thing like if you had a soda bottle that you opened and then all the bubbles form inside of it. That's pretty much what's happening inside of a diver's blood, which is bad, really bad. Right? It's a painful condition to go through, and it can even be fatal. So be careful of that if you ever go scuba diving, right? But real world applications right there. So I hope you found that helpful. I will see you guys in class.